Okay, here's another vodcast explaining spirometer traces and how a spirometer machine works. These are the ideas I'm going to try and cover, so pause this and make sure you can revisit these before the end of the video. So here is a spirometer machine. I'll just explain how it works. The participant puts this disposable mouthpiece into their mouth and they breathe normally. As they breathe in and out, then this chamber lid will rise and fall. As they breathe in, the chamber lid will fall, and as they breathe out, the chamber lid will rise. And that pen here will produce a wavy line on the chemograph. There are some things that you need to consider when you're using a spirometer trace, when you're using a spirometer machine. First thing is that it's a closed system, so while this participant has his nose piece on, all his oxygen is coming from what's in the machine. So you need to make sure there's enough air in the chamber and oxygen that the person doesn't die. Also, the nose piece means that he won't be able to breathe in and out through his nose, which will give a more accurate representation of the lung function. You need to then check this guy is nice and healthy. If he's nice and healthy, then he shouldn't have any other problems. There is a counterweight on the lid here. The counterweight means there's no resistance to breathing in and out. You can imagine if every time you had to breathe in and out, you were lifting up the weight of this lid, then it could be a bit of a problem. So the counterweight means that he won't have any resistance when he's breathing out. Also, there's soda lime here, which acts as a CO2 absorber. So as he breathes out CO2, the product of respiration, it gets absorbed by the soda lime, which means the trace eventually will start going down. So you end up with a wavy line as he breathes in and out, and then eventually it will start going down like that. I hope that explains it all. So you end up with this spirometer trace. Now, as he breathes out, then the spirometer trace rises. As he breathes in, the spirometer trace falls. This whole thing here is therefore one breath. So we can see that one breath takes approximately 4 seconds. This is known as the tidal volume, the amount of air breathed in and out of the lungs with one breath. So just normal breathing. So as he's breathing out normally and in normally, if you take an extra deep breath out, then this will be the expiratory reserve volume. You then take a really, really deep breath in, and that's going to be your inspiratory reserve volume. And then if you breathe back out, you go back into your normal tidal volume flow. It's important to remember that the maximum breath you can breathe in and out is known as your vital capacity. That's not all the air that the lungs can hold, because there will still be some residual volume which is contained in the bronchus and the bronchioles, which you can't remove because they have the cartilage which holds them open. So you're never able to fully get rid of all the air in your lungs. So now we're going to think about some questions they could ask you in an exam. Now I'm just guessing, and I've had a look at some past exam questions to try and guide me, but this is just stuff that you're going to have to just know and be able to apply in your exam. So if they ask you, for example, why you need to have a counterbalance, then we need to be talking about it removing the resistance for breathing. So as the subject breathes in and out, then without that counterbalance, they'd have to be forcefully breathing in and out, and therefore that wouldn't give a tidal volume, because tidal volume would be at rest rather than forcefully breathing in and out. They might ask you why you have this water in the chamber here, and you can think that this might provide more of an airtight seal so no air can enter the system or leave the system without being registered on the chemograph. They might ask you why we have these valves here. So, I mean, if you think about like how a straw works, you don't really need to have any valves on a straw. But what this does is it allows the air to circulate round past the soda lime, which obviously removes the CO2. Otherwise, what would happen is as the subject's breathing in and out, they'll just keep breathing in a higher and higher concentration of carbon dioxide, which is not a good idea, really, is it? I don't think I need to explain why. But you can think about blood pH and denaturing of enzymes if you need to. So if we think how a subject will actually have to be in order to have their tidal volume measured, we connect the person onto the mouthpiece here. That shouldn't really be moving. We connect the subject onto the mouthpiece here. So I'll draw him here. Now remember, it's important that he breathes only through his mouth, and therefore we're going to give him a little nose peg. You should remember why that's important. The subject will have to be fit and healthy in order to undertake this experiment. What we're going to do is we're just going to ask him to breathe normally and regularly because we're trying to measure his tidal volume. So we're not asking him to breathe in any way that's under forcefully or more deeply than normal. He'll provide a trace that looks a bit like this then. So the trace will have time at the bottom and it will have volume here. As they breathe out, the trace will rise up. As they breathe in, the trace will rise down. Out, in, out, in, out, in. And you can see it's starting to fall down now. Okay. In the exam, they could ask you to measure how much CO2 has been absorbed, and you could measure that by measuring this distance here that it's actually fallen. So this volume, this distance here, would be the volume of CO2 because that's how much CO2 has been absorbed by the soda lime. So if we think about how this works, they'll have a scale on the side here. Normally, most past paper questions that I've seen, it's been quite sort of simple. So they might say that this is the volume will be in like decimeters cubed. So that's important to know that. So that might be 1, this might be 1.5, this might be 2, and this might be 2.5. Sorry, it's so scratchy. And then the trace will basically normally like measure up to some of those points. So normally we'd see that the tidal volume would be something like this. And then what you do is to take an average, you'd measure at least 3 of those traces, 3 of those peaks, which will be like here to here on 3 of them, and then add them up, divide them by 3 to get an average. And you'd probably say that the average tidal volume would be probably about 0.5 decimeters cubed, give or take, 10% or so. If they show you a trace whether the volume is going down, so it's obviously showing the soda limes absorbing the CO2, the trace will look like this. So as they breathe out, and then in, and then out, and then in, out, in, out, in, out, in, out, in. Then it goes down like that. What they might ask you to do then is measure the amount of CO2 that's been absorbed, okay? So if we say this is going to be 1.5 on the scale, and then here is going to be 1.0, just for simplicity's terms, then we'd basically just measure the distance over here. So that's how much the trace has fallen. So this distance here will be the volume of CO2 in the allotted time along here. So they might ask like how much CO2 was absorbed within 1 minute, should we say, and then you can just use this distance there to do it. If they ask how much CO2 fell in like half a minute, then we just measure a slightly different amount, which would be this triangle here. So if it's half a minute, it might be just down to here. This triangle's terrible. How do I go back? Oh, can't do that. I'm just going to use this rubber. More colours. So for half a minute, it would be this sort of distance here that we'd be measuring. And then obviously, like, you would measure it directly to that line, so make sure the triangle touches. Right, well, I hope that helps. If you have any other questions, you can Moodle me or speak to your teacher in lesson. Good luck.